When you think of a particle accelerator, what comes to mind? Probably a gigantic machine, like the Large Hadron Collider in Switzerland, which is a massive 17-mile-long ring. These incredible facilities are used to produce intense X-rays for studying everything from new drug molecules to advanced materials. But what if I told you we could shrink one of these behemoths down to the size of a microchip? That's exactly what my colleagues and I have discovered in a new research project. We've figured out a way to create a powerful X-ray source that could literally fit on your tabletop. Instead of giant magnets and miles of tunnels, our design uses tiny, hollow structures called carbon nanotubes, each one smaller than the width of a human hair. Here's how it works. We came up with a concept that relies on a special kind of light, which we call twisted light. Imagine a laser pulse that swirls like a corkscrew as it travels. When we fire this twisted light into one of our carbon nanotubes, it creates a powerful swirling field inside. This field grabs onto electrons and accelerates them, forcing them into a tight spiral motion. As these electrons spiral together in sync, they release a brilliant, focused beam of X-rays. Essentially, we've created a microscopic synchrotron. The same physics that powers those city-sized accelerators is now happening on a nanoscopic stage. So, what are carbon nanotubes? These incredible little tubes are made of carbon atoms arranged in a hexagonal pattern, like a rolled-up sheet of honeycomb. They're unbelievably strong and can handle electric fields, hundreds of times more powerful than conventional accelerators. We can even grow them vertically, creating a forest of perfectly aligned hollow tubes. This unique structure is the perfect environment for our twisted laser light to work its magic. The circularly polarized laser fits into the nanotube structure like a key in a lock. Our simulations show that this interaction can generate electric fields of several trillion volts per meter. That's way beyond what any current accelerator technology can achieve. This kind of performance could completely change who gets to use these cutting-edge X-ray sources. Right now, scientists have to apply for limited time at large national facilities, often waiting months for just a few hours of beam time. It's expensive and inaccessible for many. But our tabletop accelerator could bring this power directly into hospitals, universities, and industrial labs wherever it's needed most. Think about the possibilities. In medicine, this could lead to much clearer mammograms and new imaging techniques that show soft tissues in incredible detail without needing contrast agents. For drug development, researchers could analyze protein structures right in their own labs, dramatically speeding up the creation of new therapies. In materials science, it could allow for high-speed, non-destructive testing of delicate components. Of course, our research is currently at the simulation stage. We've shown the theory works. The next big step is to build a prototype and prove it experimentally. The exciting part is that all the necessary components, like powerful lasers and precisely made nanotubes, already exist in advanced labs. What truly excites me about this isn't just the incredible physics, but what it represents for science. While we'll still need massive accelerators to push the boundaries of discovery, this technology could democratize access to world-class research tools. It could put the power of a synchrotron into the hands of thousands more scientists and innovators around the world. The future of particle acceleration isn't just about getting bigger. It's also about getting smaller, smarter, and more accessible for everyone. Thanks for watching. If you found this as exciting as I do, be sure to like this video and subscribe for more updates on the future of science and technology.